Hi, my name is Carlos Pinheiro. I'm a PhD candidate at Universidade Traz os Montes de Alto Douro. Thank you for participating in this survey that starts to validate an ontology for a solution to apply data mining techniques to obtain an enterprise architectural model. First of all, to give a context of the problem, due to the speed of change we have seen, enterprise architects need to respond faster and faster to business changes. Moreover, updated models may lead to wrong architectural decisions, so enterprise architects need to discover, document, and keep updated their current architectural model. Additionally, we have to consider that manual modeling is time-consuming and error-prone task. So at the end, our objective is to develop an approach for enterprise architectural modeling based on events collected using API gateway logs as data source. We also need to make clear some key definitions. Enterprise architecture is a coherent set of principles, methods, and models useful to design an organizational structure. It encompasses all business capabilities, activities, information, and technology of an enterprise and seeks to understand and communicate how business and IT components are related to each other and to the business strategy. Ontologies typically describe concepts, relations between these concepts, and constraints that indicates how to interpret these relations. It may be a domain reference ontology, which are solution-independent conceptual models that aim to create a clear and precise description of a domain for the purpose of learning, problem-solving analysis, and communication. In contrast, operational ontologies are designed to focus on computational properties for data interoperability and usage. So I'm going to present a domain reference ontology here. To present the ontology result in its application, we introduce a hypothetical case of an online buying process on an e-commerce website. The user navigates to search for products, add to cart, remove it from the cart, so on. When they finish their search, they go to the cart checkout. If not previously authenticated, they have to create an account and log on. Then confirm the cart checkout and form payment data. After authorizing the payment with the payment provided, the e-commerce system sends the order to the logistics system to deliver the product to the user. In some step of the process, the e-commerce system interacts with some API operations. Back into the ontology, this may choose the core concepts. The kind API call records the most relevant attributes for each call. Timestamps that record the exact moment an API request hits the API gateway. Result status that indicates success or failure. URI indicates the internet address used to call the API name, and resource name. This last is the name of the resource of the API called. The API are called by an authorized consumer app, representing a partner identified through the attribute client ID. The relator caller represents partners that make requests to API calls. An API call also has one or more API operations and also one or more service destinations. That is the service called by API in the backend or the external service provider. API operations and service destinations extend the kind service identified by its endpoint host. The kind resource represents the class of objects handled by API, and it can be seen as entity data structures with the API domain and API call payloads. To build the process view, the relator frequent temporal correlation represents the data mining process that correlates API requests in a temporal sequence, considering each API request as an atomic process event, then classifying them as antecedent and consequent activities. The candidate activities are identified and grouped considering the same consumer app, the API resource ID, and repeat the attribute values in the API call payloads. Thus, it's possible to identify the sequence candidates and assign to each sequence a case ID, building individual instances of process. The process instances are grouped in the collective process based on the first and last activities. So the inner different path sequence are seen as a variation of the same process group in the collective process. Then, view based on Archmate application usage viewpoints is created with the process mapped to Archmate process into this view and aggregated to the group element process layer. Based on the example we have presented before, the right side of this figure depicts the resulting in Archmate model. Another viewpoint is the service dependency view. For that, the frequent API service correlation represents the data mining techniques applied to identify frequent associations between API exposed in API gateway and API provided by backend applications. It correlates two service components, identifying those that play the role of the antecedent service that frequently calls a consequent service. So the relation between these services are individuals of the kind component dependence. The collective component relations groups these dependencies in context based on the app name and API name. Thus, an API service dependency view is created in Archmate from the attribute dependent service is extracted an Archmate element application service that it's grouped into the backend service layer. The API linked to this backend service are mapped to application interfaces grouped into API layer. The relation between these application service and application interfaces creates an assignment relation in the Archmate model. Then the same logic is applied to the attribute app name that is mapped to business actor. Then this figure presents the mapping of the concepts to Archmate model based on our e-commerce example with the API layer and the service layer. This part of the ontology, the frequent data domain correlation represents the association rule mining technique that extracts frequent correlations based on repeated values in resource attributes. The data objects are directly related to the data structures of the API call within the kind resource. The repeated attributes of data objects are used to measure the strength of the relation. Then the entities are mapped to an application data object element in Archmate, and the domain is also mapped to another Archmate data object that aggregates the entities. This figure shows the mapping of a data object identified by the mining process to Archmate data objects. In the example, identify the entities cart, products, orders, and payments grouped in the API domains, e-commerce API, and payment API. So that is, and thank you for your attention.